Swayam Prabha. Digital India. Educated India.
In the previous lecture, I was deriving for you the balance equation in a spherical coordinate system. Okay, as I told you earlier, in a spherical coordinate system is used when you want to solve problems in which the boundaries have spherical symmetry. In those cases, you would like to the boundary to be a surface of constant coordinate. And one of the surfaces in a spherical coordinate system is of course at a constant distance from the origin. If you have a spherical shell in as a boundary, the distance of every point on that from the origin is a constant. And therefore, one would prefer to choose the distance from the origin as one of the coordinates. And that is what is written as the radial coordinate over here, the distance from the origin. Okay. You need two other coordinates, and these two are angles. The angle from the z axis, any arbitrary axis can be chosen as the z axis depending upon the symmetry of the problem. The angle from the z axis is what is called theta. Okay. So, theta is equal to 0 is the plus z axis. When you go through an angle of pi, you reach the minus z axis. So, theta is equal to pi is the minus z axis, and theta varies from 0 to pi. And phi goes from 0 to 2 pi, because phi is the angle made by the projection of the radius vector onto the xy plane. That projection makes an angle phi with respect to the x axis. So, therefore, the projection is given by r sin theta and the z axis is given by r cos theta. Therefore, x is r sin theta cos phi and y is equal to r sin theta sin phi. Okay. In this case, you choose a coordinate system in which the surfaces are surfaces of constant coordinate. Okay. So, there has to be one surface at r and one surface at r plus delta r, one surface at theta, the other surface at theta plus delta theta, one surface at phi and the other surface at phi plus delta phi. Okay. Along the r direction, if you increment by a small distance delta r, the actual distance moved is delta r itself. In the theta direction, if you increment the angle theta by a small distance delta theta, the actual distance moved is r times delta theta. Okay. And in the phi direction, if you increment the angle moved by a small increment delta phi, the actual distance moved is the radius times delta phi. Radius in this case is r sin theta, okay, of the projection onto the x axis. So, therefore, for this case you get r sin theta times delta phi, which means that the surface areas of this are also functions of position. The surface at r, okay, is equal to the distance in the theta direction times the distance in the phi direction. Okay. And that does vary with radius, because the surface area of a spherical shell is going to depend upon the distance from the center. Okay. The surface at theta is equal to the distance moved in the r direction, okay, is equal to the distance moved in the r direction times the distance moved in the phi direction. Okay, that is the surface area of the surface at the location theta. Similarly, at theta plus delta theta. Okay. And then you have two surfaces at phi and phi plus delta phi. The total volume is the increments in all three directions. Okay, the distances in all three directions. And using these surfaces for this differential volume, we will write down the balance equation. So, I have written it down here, okay, the change in concentration at time delta t times the volume, okay, is equal to the flux in the r direction at r, that is what is coming in, the flux in the r direction at r, times the surface area of the surface perpendicular to that direction, which is basically the increment in the theta direction times the increment in the phi direction, okay, minus what goes out at r plus delta r, okay, times the distance in the theta direction times the distance in the phi direction is the surface area, okay, and all of these have to be multiplied by delta t to get the change in mass. Similarly, in the theta direction, at theta the flux has to be multiplied by the surface area, the distance in the r direction times the distance in the phi direction, and similarly at theta plus delta theta, and similarly at phi and phi plus delta phi. We had taken this and we had divided throughout by the volume times the time, okay, and we had got an equation of this form. Okay. Now, I will simplify this equation. Okay. The left side is as it is. Okay. Okay, the left side is as it is. Okay. On the right hand side, if you look at the first term here, okay, if you look at the first term here, okay, I can cancel out the increments, okay, I can cancel out the increments theta, okay, and sin theta delta phi, okay, because these do not vary as r varies. Okay. Sin theta does not change as r varies, and delta theta and delta phi do not change. Okay. So, those I can cancel out, okay, and I will get at r, okay, times r square minus whole square. Okay. I have cancelled out sin theta, delta theta and delta phi. These do not change as I am varying r. Okay. The second term, I can cancel out delta r. Okay. I can cancel out delta r, okay, since delta r does not change as theta has changed. Okay. And I can also cancel out this delta phi here. Okay. Delta phi can be cancelled out, and then I have a factor of r here, okay, and this r once again, okay, is not changing as theta changes. However, sin theta is changing, okay, sin theta is changing. Okay. Therefore, I cannot just cancel out the sin theta terms here. Okay. So, if I do that, I will get plus 1 by r sin theta, okay, delta theta into u theta c plus j theta at theta times sin theta minus u theta c plus j theta at theta plus delta theta sin of theta plus delta theta. Okay. And on the final term on the left here, I can, as you vary phi, r does not change, delta r does not change, delta theta does not change. Okay. Therefore, I can cancel out all of these, okay, delta r, okay, r delta theta, okay, delta r and r delta theta. Okay. So, I will get into u phi c plus j phi at phi minus u phi c plus j phi at phi plus delta phi. So, that is the difference equation simplified, and now I take the limit delta t, delta r, delta theta, delta phi going to 0. Okay. And the differential equation you will get will be partial c by partial t. Okay. I have urc plus jr at r minus urc plus jr at r plus delta r, okay, times r square. Okay. So, this is equal to minus 1 over r square d by dr of r square into urc plus jr. Okay. If it had been the value at r plus delta r, if it had been the value at r plus delta r minus the value at r, I would have got a positive sign. This is the value at r minus the value at r plus delta r. Okay. So, I have a negative sign here. Okay. The second term is minus 1 over r sin theta, okay, d by d theta of, I have a sin theta within the brackets times u theta c plus j theta. Okay. And the last term I have plus 1 over r sin theta, okay, delta by delta phi of u phi c plus j phi. This should also be with a negative sign. Okay, this should also be with a negative sign. Okay. So, these are the three terms that I get. Slightly more complicated differential operator. The reason for that is because those surface areas are changing with radius. Okay. That was what gave you these terms over here. Okay. This r square and r plus delta r square. The mass transport is equal to the flux times the surface area, and as the surface area changes, okay, you have to take that also into account in the, to find out the total rate at which mass is being transported. Okay. Once again, I can take the convection terms to the left and the diffusion terms to the right. Okay. Partial c by partial t plus 1 by r square d by dr of r square cur plus 1 by r sin theta d by d theta of sin theta c u theta plus 1 by r sin theta partial of c u phi by partial phi. Convection terms on the left, the diffusion terms on the right. If you recall, we had written this same equation in vector notation as partial c by partial t plus del dot u c is equal to minus del dot j. Okay. This equation has the same form, okay, as the concentration equation in Cartesian coordinates. If I were to define, okay, the divergence operator, okay, the divergence operator del dot j in this case is equal to 1 by r square d by dr of r square jr plus 1 by r sin theta plus 1 by this is the divergence of the flux vector if you define it this way, and similarly for the velocity times concentration for the convective flux you get the same relation. And this del dot u c is defined as note that as expected this divergence operator has dimensions of 1 over length. Each term in this divergence operator has dimensions of 1 over length because it is a divergence, it is one derivative with respect to spatial position. Okay. Now, This flux can be written once again in a Cartesian coordinate, in a spherical coordinate system. Okay. In a Cartesian coordinate system, if you recall, this was quite easy, okay, minus d or okay. We had Jx is equal to minus d partial c by partial x, Jy is equal to minus d partial c by partial y, and Jz is equal to minus d partial c by partial z, okay, in the Cartesian coordinate system. Okay. In a spherical coordinate system, it will not be just derivatives with respect to the angles, because the derivative with respect to an angle does not have dimensions of inverse of length, okay, whereas you would expect all terms in the flux to be a diffusion coefficient times the derivative with respect to position. So, you have to actually take the actual distance moved. Okay. So, therefore, Jr will be equal to minus d times partial c by partial r, because the actual distance moved is delta r. When you go from r to r plus delta r, the actual distance moved is delta r. Okay. The flux in the theta direction is going to be equal to minus d. Okay. When you go a small distance in the theta, a small increment in the theta direction from theta to theta plus delta theta, the distance moved is r times delta theta. Okay. Therefore, you will get 1 over r, okay, partial c by partial theta. Okay. Similarly, in the phi direction, when I move a small distance in the phi direction, the actual, I am sorry, when I change the phi angle by from phi to phi plus delta phi, the distance moved is actually r sin theta delta phi, okay, as I showed you. Okay, the distance moved is r sin theta delta phi, because the length of the projection is r sin theta, that times the angle. Okay. So, I will get minus d by r sin theta partial c by partial phi. Okay. And these expressions I can insert into the differential equation on the right side. Okay. So, on the left side I had partial c by partial t plus 1 by r square d by dr of r square c u r del dot cu. Okay. On the right side I had, okay, minus the divergence of the flux. Okay. So, I have, okay, minus 1 by r square d by dr of r square into minus d partial c by partial r. Okay. That is Jr. Okay. Okay. And minus the second term is 1 by r sin theta delta by delta theta of sin theta into j theta, okay, sin theta into j theta, which is minus d by r partial c by partial theta. Okay. And the third term is minus 1 by r sin theta, okay, d by d phi of, okay, j phi, okay, which is given by this, okay, minus d by sin theta r sin theta partial c by partial phi. Okay. You can simplify each of these terms. Okay. If you assume that the diffusion coefficient is independent of position, okay, if you assume that the diffusion coefficient is independent of position, okay. So, this first term just becomes equal to, okay, I take the d out, okay, the minus and minus cancels, and I will get d into 1 by r square d by dr of r square times dc by dr. Okay. Minus I have a d by r here. Okay, so I have taken the d out and I have cancelled the negative signs. So, I will get a plus here. This d has come out over here. and I can take this r out. So, I get 1 over r square sin theta. Okay. Okay. You have sin theta partial c by partial theta. Okay. And once again I take the d out on the last term. Okay. I get a plus sign here. And 1 over r square sin square theta comes out, sin square theta. So, let remove this, and this term becomes partial square c by partial phi square. Okay. So, this is the right side. Okay. I have simplified it by just inserting the expression for the fluxes in. Okay. And once again, if you compare it with the equation partial c by partial t plus del dot u c is equal to d del square c. Okay. This gives me the expression for the Laplacian operator. Okay. In a spherical coordinate system, del square is equal to 1 by r square d by dr. Okay. So, let me just put this as that is the Laplacian of the concentration. Del dot u c is equal to 1 by r square d by dr of r square u c. Sorry. And the equation for the gradient, okay, j is equal to minus d grad c is equal to minus d into partial c by partial r plus, sorry, with these definitions, I can write the conservation equation as partial c by partial t plus so the equation when written in this vector notation looks the same. Only thing is that the definitions of these, the Laplacian here, the divergence here, and this gradient here, these have changed in this spherical coordinate system. Okay. So, this is the conservation equation in a spherical coordinate system. Okay. Okay. So, if I write it again for you, partial c by partial t plus okay, so that is the conservation equation in a Cartesian coordinate system. Seems a little complicated, but the procedure for deriving this is exactly the same as a Cartesian coordinate system. You have to identify what are the three coordinates, what are the surfaces of constant coordinate, what are the distances moved along the three directions when these coordinates are incremented by a small amount. Construct a differential volume whose surfaces are surfaces of constant coordinate. Identify the surface area of each surface. There will be 6 surfaces in 3 dimensions. Identify the surface area of each surface, the total volume. Change in mass is equal to mass in minus mass out plus sources. Take the limit as the increment in each coordinate goes to 0. You will get a differential equation. One has to be careful when the surface area depends upon the coordinate. In that case, you cannot just cancel the coordinates themselves, because the surface area is varying as the coordinate changes. Provided you do that correctly, you will get the correct differential equation. From that, you can get back what are the definitions of the divergence, the gradient and the Laplacian in this coordinate system. So, I have shown you how to get balance equations in Cartesian in a cylindrical. Cylindrical is slightly complicated, the procedure is exactly the same. Next, we will look at how to solve these balance equations in limiting cases where convection is dominant, where diffusion is dominant. First, when diffusion is dominant. If you recall, the diffusion term is the Laplacian of the concentration field. So, when diffusion is dominant, the Laplacian of the concentration field is just equal to the sources. So, the procedures for solution basically reduce to procedures for solving the Laplacian. Convection dominated regime, this you would expect to be 0. You can neglect diffusion, but I showed you in the last lecture, even when convection is dominant, diffusion will be important near surfaces. You have to identify the length scale of the region near the surface where convection is important, and then find out what is the concentration field within that region. We will start looking at diffusion dominated flows in the next lecture, where we can neglect the convective terms. So, that we will start in the next lecture. The solution of the Laplace equation in most cases just is done by separation of variables. I had shown you previously how to do separation of variables in the Cartesian coordinate in one direction. In 3 directions, the procedure is very similar. I had shown you how to do it in a cylindrical coordinate system. In this series of lectures, I will show you how to do it in a spherical coordinate system. And physically, what do those separation of variable solutions physically mean? And then we will go on to convection dominated flows, where we will use boundary layer theory to solve for the concentration field in thin regions near surfaces where diffusion and convection are comparable. So, we will start solving problems diffusion dominated flows in the next lecture. I will see you then.